Hello everybody. For this video, we're going to talk about section 6.2, which is trigonometric substitution and trig integrals. Now, we're going to break this section into two pieces. The first half is trigonometric integrals. It's just some interactions between trig functions. And obviously, this doesn't cover all the cases, but they should give you a decent idea on how to tackle some of these trigonometric integrals. So let's get started. We're gonna have 5 different cases, the ones that we want to focus on. Mainly is the interaction between sine and cosine and secant and tangent. These are kind of interesting, mostly because they kind of fit together in a certain way, due to the fact that the derivative of sine and cosine are just of each other with some, change in sign. And secant and tangent also have this interaction where the derivative is very closely related to the actual function. Anyways, without further ado, let's take a look. We're going to start by the cases with sine and cosine. So for the sake of notation, we're going to do sine of m, cosine of n. So m is the power of sine, n is the power of cosine. Now I did say these are for natural numbers. Mainly, that's probably the easiest way to describe non-zero integers. So we could take the power to be 0, right? Zero power just means the term doesn't exist, like did not show up in the integrand. Nothing too special here, but basically we don't want to necessarily deal with negative exponents. Uh, Whenever you do see negative exponents for exponentials, for trig functions, we essentially want to leverage the fact that we have the reciprocal identity to rewrite them into another trig function, right? To get rid of that negative exponent. Anyways, so case number 1 here is the interaction between sine and cosine, and this is relatively simple. This breaks down to 2 subcases. Subcase number 1 is m or n is odd. Either one is odd is fine, or both is odd is fine. Either way, this is the easier case. In this case, we break off the odd power, and then we use the other function as a u substitution. If both are odd, then you can choose whatever you want, whichever function that you want to use. I would still use u equals to sine, because this way the derivative, right, du is just going to be cosine instead of having an extra negative. Whatever you can do to make your problem a little bit simpler. So let's take a look at this case here. We have sine of 5, right? Sine to the 5 power and cosine to the second power. So obviously sine here is the odd one. So I'm just gonna go ahead and break off a piece here. Sine to the 4x, sine x, cosine square x dx. I guess write your dx's, okay, because the second half of this section is where you will get in a lot of trouble if you do not write the dx. Get in that habit now. After rewriting this way, according to the hint for the case here, I'm going to let the other one, so I broke off a piece of sine, right? So I'm going to let the cosine as u. So here, basically u equals to cosine x, and if you take the derivative on both sides, then you get du equals to negative sine x dx. So again, if you have to choose cosine through u, then you have to be careful of that negative, right? So multiplying that negative on both sides, we get negative 1 times du equals to sine of x dx. Okay, so from here, we can then do a little bit of substitution. I know I want to get rid of all of the sine, right? So I can make that substitution. I want to get all of the sine and rewrite them as cosine. But over here, I have a sine to the 4s, which is not very easy for me to get rid of. But what I can do is I can rewrite that a little bit. I'm going to rewrite that into sine square x quantity squared. And then since I'm already here, I'll go ahead and rearrange this here. So I'll put the cosine square x first, and then sine x, and then dx, right? Just so I can match up that sine x dx there. That's the only reason why I rearranged it. But the important part is still to write that sine to the fourth as sine squared squared. And now I can use the Pythagorean identity to rewrite sine square x as 1 minus cosine square x square, and then cosine square x sine x dx. Now I got everything in term of sine cosine, where there's only one piece of sine left. Right, I need that piece of sine here just because I need that du somewhere. But I want to get rid of everything else so I can make my substitution. So at this point, I can go ahead and do that substitution. This becomes the integral of 1 minus u squared, right? Because cosine is equal to u. And then don't forget that squared. And then another u squared. And then the sine x dx becomes negative 1 du. Okay? So at this point, you just have a polynomial. We can, go ahead and FOIL this part out, right? We know how to deal with polynomials. So it's just 1 minus, I guess, 2u squared plus u to the fourth times u squared times negative 1 du. I can bring that negative 1 out. I tell you what, I will go ahead and just bring that out. Negative 1 integral, and then don't forget to distribute the u squared as well. U squared minus 2u to the fourth plus u to the sixth du. And now the integral simply becomes negative 1 u to the third over 3 minus 2u to the 5 over 5 plus u to the 7 over 7 and plus c. Okay. At this point, we back substitute into x. And might as well go ahead and distribute in the negative 1 as well. So we get negative 1. I guess I can just put negative. Negative cosine, u is cosine, right? Cosine cubed x over 3 plus 2 over 5. Maybe let me keep it in the same format. Plus 2 cosine to the 5 of x over 5 plus minus cosine to the 7th over 7 plus c. And I know, it's the usual thing. I'm supposed to distribute the negative. It'll become a negative c, but then you just rewrite that into a positive c anyways. Again, it's the same thing that we've been doing with that constant c. We don't have to worry too much about that detail there. Feel free to use k if you really like that extra step of transition. But anyways, this is it for that integral. It's really not too bad once you get used to it. It's just basically remember these kind of cases, especially the easier cases or easier sub cases of both these cases is not too bad to work through. Okay. Moving on to the next case, right? If subcase number 1 is either m or n are odd, or both, then that means the other case has to be m and n are both even. So nothing is odd, right? This is actually the slightly harder case. This is where you have to leverage the power reducing formula. And by the way, all these formulas are in the identity cheat sheet that I've already posted. So if you needed this, take a look. Anyways, there's actually a little bit of special case here too. On top of that, when m and n are both even, in fact, are both the same. In this case, when m is equal to n, right? Both of these are squares. We can actually use the double angle formula to simplify the integral first, so we don't have to go through the motion and do all of that extra work. Now, you can just directly jump in and hit it with the power reducing formula for sine and cosine, and you will work out. It just, why not simplify things a little bit first? I guess it's worth writing this down here. So basically here, let me write it on the side here. We call that 2 sine x cosine x equals to sine 2x, right? That's the double angle formula for sine. So all I have to do here is to divide 2 on both sides. I get sine x cosine x equals to 1/2 sine 2x. So now if I go ahead and square both sides, I will get sine square x cosine square x equals to 1/2 squared is 1/4 sine square 2x. Okay, so basically, whenever the power of sine and cosine are the same, you can leverage this to kind of simplify your expression a little bit into a single term of sine. So the integral just becomes the integral of 1/4 sine square 2x dx. Okay, and from here I can go ahead and take out that, the 1/4 here. Okay, and I have sine square 2x dx. And now I once again hit it with the power reducing formula, right? You can't really get away with that here. You will get 1/4 integral 1/2. The power reducing formula here for sine square is going to be 1 minus cosine 2 times the angle in between. So it's going to be 2 times 2x dx. Okay, so again, the power reducing formula is on the chart here. Since we're here, is sine square x equals to 1/2 1 minus cosine 2x. Okay, and again, the power reducing formula and the double angle formula for cosine is really two sides of the same coin. They just derive from each other. Anyways, so I can go ahead and pull out a 1/2, so it becomes 1/8 on the outside. And then the integral becomes 1 minus cosine 4x dx. Okay, and if you're comfortable doing the integrals basically as we practice on the the first day or sometimes during the integration by part sections, then the answer here is pretty easy to write down. You just have 1/8 times x minus 1/4 sine of 4x. Okay, plus c. Oh, yeah, we'll go ahead and write it like that, but I mean, technically, should be something like that, right? And then you just go ahead and distribute the 8, the 1/8 that is. You have x over 8 minus 1/32 sine of 4x, and then plus c. And that right there is your final answer. In case you're not quite yet comfortable with that, let's go ahead and take a quick detour though. So you got, you want to break this apart, 1/8 integral of 1 dx minus integral of cosine of 4x dx. Okay, and that of course is 1/8. Let me separate these two. Of course, 1/8, and then this integral is easy. The first integral is easy. You just x minus this one though. Even if you were to use the same trick as before, you have to do integral of 1 over 4 times 4 cosine of 4x dx. Right? And now you can pull out the 1 over 4 and then just do that integral, which is sine of 4x. Okay, and don't forget the plus c. So that's how I got that value. But again, you can definitely jump to that state, jump to that result at this stage of the game, and I'll be perfectly okay with it. However, what I do want to kind of stress a little bit here is that there's actually a lot of constants being worked out in this problem, right? From the initial simplification, there's already like weird constants happening, on the side here and there. There's a issue with negatives, right, that comes around. Not in this particular problem, but like, for this kind of integral in general, there's a random negative that pops out. So again, guys, the bookkeeping in this class is some of the most important things that you have to be aware of. Okay, so do these very carefully, do this very slowly if you have to, and chances are even in my solution there's going to be issues. Okay, so I need you to kind of look at these with a not with a trusting eye, right? You want to almost check my work as you go along, and you want to check your own work, right? That's the the right attitude as you approach this kind of questions. Okay, so let's move on from this case then. Okay, going on big case number 2 here. Now we're working with the interaction between tangent and secant. Again, they have the same issue here, except for this time the format is a little bit different, right? The derivative of tangent is secant square, whereas derivative of secant is secant tangent. So it doesn't quite follow the same format, so we have to break this down into different cases. This version we have 3 subcases, mainly focused on the exponent of the secant. So the easy case, the first case, is when the secant has even power. So when n is even. Okay, when n is even. In this case, we're going to go ahead and break off 2 powers of secant and then use u equals to tangent. So here for this problem, we're going to go ahead and do tangent 7x, tangent to the 7x times. We're going to break off 2 p's. So I got basically secant square and secant square here. And don't forget that dx. I'm going to use u as tangent. So here we'll do u equals to tangent of x. And of course from here, du equals to secant square x dx. Right, that's why we break off 2 copies of secant. Okay. And that just means I need to write everything in terms of secant, in terms of tangent with your integral, except for the 2 copies of secant, which means from here, actually, let me write this way, from here to here, I'm going to rewrite this integral into tangent to the 7th x, and then this secant, the first secant, I'm going to rewrite that using the Pythagorean identity again, right, the other version of it, which is tangent square x plus 1, because that's what I did here. And then the rest copy and paste, secant square x dx. And now I'm ready to hit it with my substitution. I got the integral. Tangent is u, so just u to the 7th power times u square plus 1, and then secant square theta d, secant square x dx is just du. And now I distribute that polynomial, u to the 9 plus u to the 7th du, and very easy integration here. So u to the 10th over 10 plus u to the 8th over 8 plus c, and you just have to back substitute. So u is equal to tangent, so the answer is just simply tangent 10x over 10 plus tangent 8x over 8. And again, don't forget that plus c. Okay, so this case is like the easy case for sine cosine. Ultimately, this comes down to a nice application of the Pythagorean identity. As long as you remember how to do the u sub, or which part to use for u sub, you should be fine. This next case is actually very similar. This is the case where m and n are both odd. In this case, we're going to go ahead and take out one power from each tangent and secant, and then use u equals to secant. Again, the reasoning behind that, of course, is because the derivative of secant is secant tangent. Okay, so let's see how that plays out. This problem, tangent square x, right? Break off one copy. Secant, secant to the 4th x, and then we'll have tangent x secant x dx. Okay, now here I'm gonna go ahead and let u equals to secant x, then du equals to tangent x secant x. Doesn't really matter which one you write first, right? Tangent x secant x dx. Now just to get everything from tangent to secant, all I have to do again is to use the Pythagorean identity, turn that tangent square into secant square x minus 1. And then I have, secant to the 4th x, tangent x secant x dx. Okay, and now I'm ready for my substitution. I will just get the integral of secant is u, so u squared minus 1, and secant to the 4th becomes u to the 4th. Tangent x secant x just becomes du. Okay, so basically plays out the same way as last problem at this stage. So distribution, I'm gonna get u to the 6th minus u to the 4th, du, easy integral here, u to the 7th over 7 minus u to the 5 over 5 plus c, and just remember that u is equal to secant in this example, so secant to the 7th of x over 7 minus secant to the 5th of x over 5 plus c. Okay, and that is your answer for this problem. Now, again, these two examples are these two subcases are the simpler cases, and they're fairly easy to do as long as you remember these cases and remember how to basically how to handle them, right? Like how to break off these pieces. The last case here is a very challenging case in general, or is harder at least compared to all the other 5. Well, I guess in some sense this is more comparable to the second case of the sine cosine version. Anyways, this is a version where n is odd. In other words, the power of secant is odd. This is different because you actually don't use any of the previous techniques. You actually focus on integration by part. So this is special, and we have to use integration by part. In fact, majority of the time, this one will come out to be that weird version of integration by part that I have it in a separate video. So if you watch this one first, or might have to see the other one for more explanation, but I'm going to try to write it as best as I can. Here we go. The key to do this is to take 2 powers of secant and set that as your dV, and whatever you have left, set that as U. So if you rewrite this real quick, you get the say the integral of secant x secant square x dx. A little bit bigger here. And what we're going to do here is to let that be U, let that be dV. Okay, so now U equals to secant x, then du equals to secant x tangent x dx, and then dv equals to secant square x dx. So v is equal to tangent x. Now, once I have this set up, I'm ready for my integration by parts. So here we go. This is equal to uv. Actually, maybe move this just a little bit further down here. Okay, so this right here is equal to uv. So it's just gonna be secant x tangent x minus v du, integral v du, minus tangent x, and then du is secant x tangent x dx. Okay, so v du. We shift this down a little bit more here, just so I can kind of box that out a little bit. Now let's just clean this up a little bit. We got secant x tangent x minus. What we have here is we got 2 copies of tangent, right? So that's just tangent square x secant x dx. And unfortunately, this also falls under the fact that secant is odd, right? Because it's secant to the first power. And it's actually not quite obvious which one is easier to do. The original secant cubed, or here tangent of x. Because you can't actually break off 2 copies of secant as well, right? You cannot do that anymore because you only got 1 copy. So how do you handle this kind of problem? Well, we actually have to use tangent, right? We want to use the Pythagorean identity to rewrite that into secant. So here we go. We have tangent x, secant x tangent x minus the integral. This tangent square x becomes secant square x minus 1, and then times the secant x dx. But you kind of see something kind of interesting, because after you distribute, you're actually going to get secant cubed x plus secant x. Jump the gun there a little bit. This is still minus at this point. Minus secant x dx. Right? If you just kind of imagine, distributing the secant x here. What kind of then becomes a little bit interesting here, in case this is the first time you see this technique, is that if I break up that integral, I get a integral of secant cubed x dx plus the integral of secant x dx, right? Because the double negative becomes the positive here. Okay, I simply just distributed. You can kind of imagine that negative. But what is interesting here is I actually got another copy of secant cubed x, which is what I started with, right? Which is what I started with. So, this is the situation. Wait, how do I squeeze this a little bit more here? Yeah, so this is the situation I'm in. I'm actually in, if you kind of trace after what we did so far, so just erase this. If you kind of see what we did so far, we started from here. We started from here. And all of these equal signs later, we end up here. In fact, the last one, I should just write out the integral, because the last one is a known integral from Calc 1. I'll tell you what, why don't I do that? Yeah, just write one more line here, and then I'll format it a little bit better. Secant x tangent x minus the integral of secant cubed x dx. And again, this is a well-known integral. This is actually just plus ln of secant x plus tangent x. Okay, now I'm not writing that plus c just yet, just because I have a plus c inside the integral of secant cube as well. But I do want to just remind you that this is a well-known integral. Let me just take this whole thing and make it just a little bit smaller so I have more room. What is the name? I don't know what happened here, but like we can rebuild, we can rewrite. There we go. Okay, so what we have so far is we started here, and after all of that equal sign is supposed to equal to this. Okay, but now I'm kind of in a loop, because the integral I started with, obviously I only did all these techniques because I don't know how to solve it, but now I end up back at the same integral. And had I knew how to solve for that, then I wouldn't need all these techniques to begin with, right? So I'm kind of seemingly kind of stuck. But the good news is you're really not stuck, because these are two of the same quantities, right? These are the same quantities, the beginning and the end here. So what I can actually do is I can actually simply just add this integral to both sides. Okay, so maybe I can write this down here. Dang, I have to make this even smaller. How does that? I guess luckily we can zoom in this as big as we need. So that's the advantage of having this. Okay, so anyway, so what we have so far is actually the following: is the integral of secant cubed x dx equal to secant x tangent x minus integral of secant cubed x dx plus ln of secant x plus tangent x, like that. Okay, this is actually what we have so far. So now all we have to do to actually solve for the uh, secant x, you know what? Let me move this to a blank space here. Yeah, all we have to do to solve for this secant cube x is to simply subtract, or in this case add, this integral to both sides. Right, we can definitely add functions to both sides of the equation. At this point, if you want, you can think of this integral as a implicit function, right? Whatever this function is, we don't know exactly what it looks like, but it has to be a antiderivative of something. I can go ahead and add that. So what that will do is it will give me 2 integral of secant cubed x dx equals to secant x tangent x minus, or plus rather, ln of secant x plus tangent x. Okay. Now, because I moved this integral over to the other side, I should probably have a plus c here somewhere. But the point here is I can then solve for that integral simply by dividing 2 on both sides, right? So finally, there we have it. We actually have that the integral of secant cubed x dx is equal to 1/2 secant x tangent x plus 1/2 ln of absolute value of secant x plus tangent x plus c. And that long big of an answer is the solution to this integral. So a couple of things. It's a good technique here. It's a good example to kind of see this technique. But of course, if you want, you can definitely see this kind of integration by part technique in a separate video. Um, Basically, the extra examples from section 6.1. But the other thing is that this is a hard case, right? Needless to say, the amount of work we have, this is definitely a harder case here. Um, Something that you should definitely see, you should definitely be able to do, at least during like a group setting with infinite time. This is not something I'm going to, quiz you on or exam you on, almost any sense of the word. But again, this is something that you should be aware of, that is a possibility. Okay, so I'm gonna go ahead and leave this here, and we're gonna go ahead and end this video here.